So for the last talk in this session, we have Duo Wu, please, who is currently pursuing his PhD degree at Tsinghua University, and prior to that, he received his MPhil degree from the Chinese University of Hong Kong in Shenzhen. His research focus is on large foundation models and multimedia networking, and I really do look forward to hearing about the LLMs that you're working with.
Okay. Thanks for the introduction. And hello, everyone. My name is Duo Wu. I'm glad to introduce our work, NetLLM. And this is the work that we focus on using large language models to solve networking problems. And now let's get started. So this presentation will have 4 parts. And in the first part, let's first talk about why we start this research. Well, deep learning has been popular in networking. It has been applied to solve complex prediction and decision-making tasks in networking. And this figure shows the typical pipeline of the DL-based algorithms. First, we need to design a deep neural networks as the policy model. Then we have a data set or network environment to train the DNA model. And after training, the DNA model can automatically solve the networking problems. So we can deploy it for the network service. Well, however, although there are so many DL-based researches in networking, they still suffer from several limits. Well, the first is their success heavily relies on the manual design of DNA models. Unfortunately, due to the black box nature of the DNA model, the design process is often done in a trial and error manner. And this means, first we need to handcraft a DNA model, then we need to validate its performance, and if it doesn't work, we need to modify its DNA architecture. So this process will keep going and going until we have a good DNA model that works well for the network service. So the entire process can be labor-intensive and painful. Yeah. And to make things worse, the DNA model is not shareable across different networking tasks. For example, if we have a well-designed DNA model for the adaptive rate streaming service, we cannot use the same model to do cluster job scheduling. So this means that one DNA only works well for one task. So we have to manually design different DNA models for different tasks. So the model engineering overhead can be very high. And the second limitation is that the DL-based algorithms tend to achieve poor generalization performance on the unseen data distributions or environments. For example, if we train the DNA model on the stable network environments, and yes, it will achieve good performance on the same environments. However, it tends to achieve poor generalization performance on the unseen fluctuating network environments. So facing this limitation, we start to think that can we just use one model for all networking tasks with even stronger generalization? And we think that the recent large language models could be the possible answer. Now let's talk about what we want to approach in this paper, and that is make LLM do networking. Well, LLM has been popular in recent years. It has been pre-trained on massive data to absorb extensive knowledge. Then it can serve as the foundation model in natural language processing. In other words, we can use a single LLM to achieve one model for all tasks with even better performance in NLP. So yes, LLM is powerful in NLP, but the thing is, can we use it in other domains? And of course, we can. Well, researchers have recently shown that LLM is not just a master in NLP, they can be applied in other domains too. And this is because after large-scale pre-training, the LLM demonstrates some emergent abilities, such as planning and generalization to unseen cases. And these abilities prove to be transferable across domains. So this allows the LLM to be applied in other domains, such as robotic control, chip design, and protein structure prediction. So that is impressive, but can we use the LLM for networking? And I think the answer is yes, and that is exactly what we do in this paper. But why should we use LLM for networking? In fact, there are some certain benefits of doing so. First, we can use a single LLM for various networking tasks. So we no longer have to design specialized DNA models for different networking tasks. So in this way, we can significantly reduce the model engineering overhead. Besides, with the extensive knowledge of the LLM, we can also utilize its powerful capabilities to achieve better performance. So in this paper, we try to answer the following key question. Can we efficiently utilize the LLM to achieve one model for all networking tasks with even better performance? And I think the answer is yes through our framework NetLLM. And now let's talk about how we design our framework to approach our goal. Well, NetLLM is the first framework to adapt the LLM to solve networking problems with low efforts. And this means why the LLM is originally designed for the NLP community. We can wrap the LLM with our framework to make it useful for networking. And our framework consists of the following 3 modules. The first part is the multimodal encoder, which allows the LLM to understand the network information effectively. And the second part is the networking head, which can allow the LLM to generate answers for networking. And finally, there is a data-driven low-rank networking adaptation scheme, which can fine-tune the LLM to learn the networking knowledge in an efficient manner. Now let's first talk about the multimodal encoder. Well, the key challenge here is how to enable the LLM to understand the networking information. Well, we know that in networking tasks, we often collect various pieces of information for decisions. For example, in data streaming, we often collect network throughputs for decisions, which are represented as time series data. However, the network information differs from plain text in terms of data modalities. So due to the large modality gap, we cannot directly use the LLM to process the network information. So we designed the multimodal encoder to address this challenge. And our key idea is to project the multimodal data into the same feature space as text so that the LLM can understand the network information. And there are 3 building blocks inside this module. The first is the feature encoder. We utilize the existing feature encoder to inject features from the raw input data of specific modalities, such as vision transformer for image and graph neural network for graph. And we use a linear layer to map the injected features to the same feature space as text. Then we also use a layer normalization layer to normalize the features to improve the training stability. So this will result in a set of text-like features that can be understood by the LLM. Then the next challenge is how to enable the LLM to generate answers for networking. Well, to understand this challenge, let's first talk about the answer generation mechanism of the LLM. In fact, the LLM generates answers by token prediction using a language modeling output head. And here, token is a subword in NLP. And let's look at a concrete example. Well, we can see that the generated token will be fed to the LLM, and the output features of the LLM will be fed to the language modeling head. So this process will keep going and going until we have a special token called end-of-sentence token is predicted. Well, why this paradigm is well suited in NLP, it presents some limitation in the field of networking. First, from this figure, we can see that it takes multiple inferences for the LLM to generate a single answer. So this can result in high generation latency. Besides, due to the uncertainty of token prediction, the generated answers could be embedded. For example, in this figure, we can see that the generated bitrate does not match any of the bitrate versions of the encoded video, so we cannot use it to download the video. And our idea to address this challenge is just to replace the language modeling head with our customized task-specific networking head. And a networking head is, in fact, a linear output layer that can directly generate answers based on the LLM output features. Let's look at an example. Well, in this figure, we feed the output features of the LLM to the networking head, and we design the networking head to output the probability distributions of the possible bit rates. Then we can sample a bit rate from the probability distribution, then we can use the bit rate to download the video. So why this approach seems simple, it can indeed generate answer in a single inference, so it can reduce the generation latency. Besides, we can also see that our networking head can indeed guarantee the validness of the generated answers because it can directly generate answers from the possible range of valid answers. And the final challenge is how to fine-tune the LLM to learn the networking knowledge efficiently. In fact, the cost of fine-tuning the LLM can be very expensive because of the large parameter size. And the reasons are twofold. First, we know that reinforcement learning has been widely used in networking. However, it requires the active interaction between the LLM and the environments to collect the experience data set for reward optimization. And this figure shows the typical pipeline of the RL training. So if we use this pipeline to fine-tune the LLM, we will spend a lot of time having the LLM interact with the environments to collect the experience data set for training. And this process can be very time-consuming. To make things worse, if we choose to fine-tune all of the parameters of the LLM, the training cost can be even more expensive because of the large parameter size. So our DDL RNA scheme comes to the rescue, which can significantly reduce the fine-tuning cost of the LLM. Well, first, we remove the interaction between the LLM environments based on the data-driven RL technique. And to be more specific, we use an existing non-LLM policy to interact with the environments to collect the experience data set for training. And once the data set is collected, we will use it to fine-tune the LLM throughout the training process. So compared to the standard RL training, we show that this approach can reduce more than 30% of training time. Besides, we also insert some low-rank matrices inside the LLM to reduce the number of trainable parameters. And the insight behind is that the parameter update of the LLM, in fact, lies in a low-rank property. So we can use just a limited amount of parameters to approximate the parameter update needed in the LLM. And we show that compared to the standard full parameter fine-tuning scheme, our approach can reduce more than 13% of training time. Now let's talk about our evaluation. Well, in our experiments, we evaluate our framework on 3 tasks, that is people prediction, adaptive relay streaming, and cluster job scheduling. And we use the Llama 2 7B as the default LLM. And we compare the NetLLM adaptive Llama 2 with 3 state-of-the-art algorithms on each task. And in the first part of our experiments, we evaluate the performance of each method when the testing distributions are the same as training distributions. And we can see that the NetLLM adaptive Llama 2 significantly outperforms all baselines across all tasks. So this demonstrates the effectiveness of our framework in adapting the LLM for networking. Besides, it also showcases the promising potential of using a single LLM to achieve one model for all networking tasks with even better performance. And in the second part of our experiments, we evaluate the generalization performance of each method. And we can see that the NetLLM adaptive Llama 2 significantly outperforms all baselines across all cases. So this means that with our framework, we can indeed utilize the extensive knowledge of the LLM to achieve stronger generalization. And next, to understand why the LLM can be useful for networking, we investigate the importance of its pre-trained knowledge. To be more specific, we remove the pre-trained knowledge of the LLM by randomly setting its model parameters and fine-tune it with our NetLLM framework. Then we compare its performance to the regular case. And we find that without the pre-trained knowledge, the performance of the LLM is very poor. So this means that the pre-trained knowledge is indeed important for networking. And the LLM indeed contains some common knowledge that is useful for networking. And next, we also investigate the impacts of different types of the LLMs to see whether our framework is compatible with different types of the LLMs. And we can see that all the adaptive LLMs outperform the state-of-the-art on different tasks. So this means that different LLMs can be adapted to solve networking problems with our framework. And our framework is indeed compatible with different types of the LLMs. And finally, we investigate the impacts of the parameter size of the LLM, and we find a very interesting phenomenon. Well, when the parameter size is less than 1 billion, we find that the LLM perform well on one task, but poorly on the other task. So this means that the LLM no longer generalize across different networking tasks. So this means that the 1 billion parameter size could be the possible borderline of using the LLM for networking problems. Now, at the end of this presentation, we can conclude our paper with some key questions. First, can we use the LLM to achieve one model for all networking tasks with even better performance? And we believe the answer is yes, our framework, NetLLM, can do that for us. And is our framework applicable to various LLMs? Of course, our framework is compatible with different types of the LLMs. And finally, is this the end story of using LLMs for networking? And of course not. We know that our framework is not the final solutions, but we hope that it can inspire more researchers on LLMs for networking. And that's all about our presentation. Please feel free to check out our paper and give our project. Thank you.
I know we're cutting into tea time, but a couple of questions would be good.
Yeah. Hello, thank you so much for your talk. I'm Shayan Azizi, first year PhD student from here. So actually you touched on that both implicitly and explicitly. So why do you want to have a single model for all networking tasks? Because as far as I can imagine, both the engineering overhead and the data complexity, when you have specialized models, it grows linearly, but with a number of tasks. But for LLM, since I need to learn the distribution, and for different tasks, I need different features, so the data complexity exponentially grows because of the curse of dimensionality issue. So how do you see that? Like, I'm a bit not convinced of this approach. Like.
Okay. In fact, the reason why we introduce LLM in networking is one motivation is to reduce the model engineering overhead, because just like our motivation said, in the previous DL-based approaches, we need to first design a DNA model, and the architecture of the DNA model is essential to the success of our methods. And this is why there is a trend in networking to design more and more complex DNA models to achieve better performance. But due to the black box nature of the DNA model, the design process is often done in a trial and error manner, and the entire process can be time-consuming and annoying. So we want to change this situation, and we want to use the LLM as the foundation model. That is, we use it as the backbone model and without any modification on it. So then we can use it to do networking problems. Yeah.
Right. I think we need to go offline because I still think that overhead is linearly growing with the number of tasks, but the data complexity of using LLM just exponentially grows. So, but thank you so much.
Okay, thank you. Maybe we can discuss this offline.
Yeah, sure. Thank you.
Hi, thank you very much for your talk. In terms of the ABR tasks, you mentioned that for the LLM, you need to have some existing policy as the reinforcement learning training data to bootstrap it.
Yes.
I wonder what is the existing ABR policy used to bootstrap the LLM?
Well, in our experiment, we use sorry. Yes. In our experiment, we use the GNet, which is an improved version of the Pensive model, and we use it as as an existing policy to collect the experience data set for fine-tuning the LLM. Yeah.
I see. Second quick question. So usually VPO predictions and adaptive bit streaming run on client devices like mobile phones.
Yes.
So I wonder what is the runtime complexity of the LLM approach? Can it be run on device or it needs a powerful server?
Yeah, good point. And in fact, we run our experiments on A100 GPU, and we find that the runtime of a 7B model is less than half a second. And for a 1B LLM, the runtime is lower. It's about several milliseconds, I think. Yeah, but to push the LLM to the edge side, I think we need more works, and that will be the future work of our research. Yeah, thanks.
Okay, thank you.
This is Chen Jingzhou from Nankai University. I want to ask, is there a benchmark for us to evaluate the NetLLM's performance on different network tasks, or to guide us what network task we should use NetLLM?
To be honest, there are no such benchmark, but in fact, we just we classify the existing networking tasks into two categories. One is prediction task that is often solved by the supervised learning paradigm, and the other category is the decision-making task, which is solved by the reinforcement learning paradigm. And basically, our NetLLM framework can be applied to solve these two types of tasks. So if your target task falls into these two categories, we believe our NetLLM can work. Yeah.
Okay, thank you.
Oh, thanks.
All right, with that, let's thank Duo for the talk and all the speakers. And I believe afternoon tea is being served downstairs. Thank you.